Space is infinite. We are surrounded by a never-ending sea of planets, stars, and galaxies that extend out in every direction for a distance that is unfathomable to the human mind. This is what we are told at least. But when we look out into space with our own eyes, we do not see an endless glow of light. Instead, what we see in that deep infinity beyond the stars is nothing. The black void. That blackness marks an edge. Not the edge of the universe, but the end of our ability to perceive it. The distance from where we are right now to the edge of the perceivable universe is about 4612 billion light-year. And that expands out in every direction, creating a perfect sphere of observable space that is about 93 billion light-years across. A light-year is simply the distance that light can travel in the time it takes for the Earth to orbit the Sun. All light moves through space at a constant speed, and nothing can move through space faster than light. This is a fundamental ground rule of the universe. So we measure distance according to travel time at light speed. And for our sphere, that would be 93 billion years. Inside that sphere is everything we have ever known or will ever know. And down here in the very middle of it all is you and me and every human being. We are the observer. And that makes us the center of our own universe. Now, here's where things start to get weird. Because the edge that separates our cosmic bubble from the rest of the infinite universe is not black at all. It's actually a wall of light, but it's not light as we know it. This is ancient light, the first light that ever emerged from the hot, dense soup at the beginning of everything. Most people know this creation event as the Big Bang. And that's actually a really poor choice of words because it leads most people to believe that the universe began with an explosion. It didn't, and we'll get to that in a little bit. But for now at least, it doesn't really matter where the first light in the universe came from, as long as we know that it is out there at the very limits of our minuscule bubble, floating on an ocean of infinity. Now, the reason we see black when we look into space is because our eyes are just not capable of seeing light that has aged past a certain point. We have to imagine light as a series of waves like ripples on the surface of a pond. When a rock hits the water, it creates a ring of tight and clearly defined waves around the point of impact. But as the water moves away from the rock, those waves are quickly spread into wider rings with smaller peaks until at a certain distance, the wave becomes imperceptible to the eye. But that doesn't mean the impact of the rock ends at the last ripple. It continues on through the water, and you could easily measure its effect all the way to the edge of the pond. All you would need is an instrument sensitive enough to feel those small, lingering vibrations. This is why we build instruments like the James Webb Space Telescope, because it can see light in a way that the human eye cannot. When those waves of light get stretched out past a certain point, they transition out of our visible spectrum and into a range known as infrared. You've probably heard of that before. Night vision goggles can pick up infrared light, but only enough to see in the dark at relatively close distances. You can't look into space with night vision and see the light from the Big Bang. The James Webb Space Telescope can see much deeper into the infrared spectrum, which means that the blackness of space is not as black through the eyes of James Webb. It can look deep into our bubble, our observable universe, and it can see almost everything that has ever existed inside that bubble. But James Webb still can't see the edge. In the end, beyond even the most distant galaxy ever photographed, the black void remains. So then how do we know that there's light at the edge if even James Webb can't see it? Well, we have to dive deeper into the pond, deeper into light, so far. Beyond what our eyes can see, that light becomes something almost impossible to even visualize. Microwaves. We are surrounded by microwaves, and they come at us from every direction. No, not that kind of microwave. From the deepest depths of the universe, the only thing that can travel through such a vast distance of space is this incredibly faint, totally invisible microwave of light. We can't see it, but we can measure it. And hidden inside that measurement is this, the first light to ever emerge out of the Big Bang. We call it the cosmic microwave background, or CMB. And this is what we find at the edge of our perceivable universe. This is the bubble. The way we visualize the CMB is by creating a heat map. So it's not actually blue and yellow. This is just a way of showing the small variations in the microwave frequency. What this shows is that the universe is not uniform. It never was, which makes sense because the galaxies are not evenly divided across space. They are stuck together in clusters of higher densities that are surrounded by areas of lower density, just like the CMB. We'll get back to that one. But the really fundamental discovery that we can draw from measuring the wavelengths of the CMB is that it tells us the true age of the universe, or at least the age of the first light that existed in that universe. And this is where things really start to fall apart, because now we know the age of the microwave light at the edge of our bubble is 13.8 billion years old. But we also know that the distance to the edge is 4612 billion light-year. So you see what we're getting at here. If the speed of light is constant and nothing can move faster than light, then how does 13 billion-year-old light get 45 billion light-year away? Well, we have to go back to the early 20th century and the GOAT, Mr. Albert Einstein. You see, Einstein was developing a theory called general relativity, which would basically set the ground rules for how the universe works. It describes the relationship between space and time, the effects of gravity, and the speed of light. But there was one big mistake. Einstein was wrong about the size and shape of the universe. And this wasn't just him. Most scientists of the time agreed that the universe must be a static and uniform structure, just an unmoving sea of stars that all stay in the same place forever. The problem was that everything Einstein had already said about gravity would make the static universe impossible because the force of attraction would eventually pull everything together. He didn't like that. So Einstein inserted a new variable into his theory, which he named the cosmological constant, and this behaved as a repulsive force, a kind of anti-gravity that existed in the empty space between stars, and the purpose of the constant was to balance out the force of attraction and maintain the static nature of the universe. The interesting thing here is that Einstein was wrong about the static universe, but he was right about the cosmological constant. He just didn't know it yet. If we jump ahead to the mid-1920s, we meet this guy, Edwin Hubble. Hubble was the first astronomer to prove the existence of galaxies. Up until this point, the mainstream science assumption was that every point of light in the sky was a star. But they were also finding a lot of these big, bright, smudgy things in the sky that kind of looked like little clouds. And the assumption was made that these must be giant clusters of dust between the stars that were called nebula. The biggest and brightest nebula in the sky was named Andromeda. And Edwin Hubble had the idea that he was going to try and figure out exactly how far away this cloud actually was from the Earth. He was able to spot a very unique type of star inside the nebula. It's called a Cepheid variable, and they're special because they tend to pulse from bright to dim in a regular repeating pattern. So by measuring the speed of that pulse, astronomers could figure out the actual brightness of the star. Basically, the slower the pulse, the brighter the star. So what Hubble knew from taking the pulse of this star was that it must be incredibly bright wherever it is in space. But through his telescope, it appeared to be incredibly dim, which means that it must be incredibly far away. So his conclusion was that Andromeda couldn't possibly be a simple cloud of dust. It was a gigantic system of stars, and it was so far away that it had to be completely separate from our own system of stars. That was our first proof for the existence of galaxies. This tells us that the universe is not a uniform sea of light. It's made from giant clusters of stars that are all incredibly far away. Hubble's next big breakthrough was that not only do galaxies exist, but they are also moving through space, and they are moving away from us. Hubble had a colleague, Vesto Slipher, and he'd already been looking at nebulas for years at this point. And what he noticed was that the light from pretty much every single one of these galaxies was moving toward the infrared spectrum. We talked before about how the longer a wave of light gets stretched out, the deeper down it goes into infrared, moving away from our visible spectrum. Here's how that tells us that galaxies are moving away from each other. It's called the Doppler effect. Now, if you've ever watched an ambulance drive past you on the street, then you might have noticed that the noise of the siren changes as it moves. When the vehicle is driving towards you, the pitch of the siren is higher. And then as it drives away from you, the pitch of the siren gets lower. This is because the approaching sound waves are getting compressed as each blip of the siren gets physically closer. This raises the pitch. Then on the opposite side, the distance between each blip increases, which stretches the waves out, and the pitch of the siren gets lower. Now applying the exact same effect to light waves. This tells us that the longer the light waves, or the deeper the infrared, the faster that galaxy is moving away from us. Using this method, Hubble found something very weird. In all cases, the further away a galaxy is, the faster it's moving. This discovery gives us two fundamental clues about the nature of our universe. Space is expanding and the speed of the expansion is accelerating over time. Going back to Einstein, his theory of a static universe is proven wrong. We know that expansion is real, but we still need some way to explain the force that is creating that expansion. This is Einstein's cosmological constant, the anti-gravity. The only change we need to make is that the force of expansion is not equal to gravity. There is no balance. The anti-gravity is actually the stronger force in the universe. In recent years, we've come to know this force as dark energy or the energy of empty space. So, what this does is not only make the universe bigger, but it also pushes everything in the universe away from each other. Because the more empty space there is between two objects, the more dark energy there is to push them apart. And the further apart they get, the faster they get pushed. Now, where this gets really crazy is when the speed of expansion begins to move faster than the speed of light. Einstein solidified the rule that no matter can move through space faster than light, and that is still true, but it turns out that space itself gets to play by its own rules. And that means expansion can move faster than light. This is how we end up with an observable universe that first began to create light 13 billion years ago, yet has already managed to travel the equivalent of 46 billion light-years through space. Light travels at a constant speed limit while space can continue accelerating all the way out to infinity. Now, to fully understand what this looks like, we need to go back to the Big Bang, and we need to let go of the simplistic explanation that most of us received in school. You were probably told that the universe began as a cosmic egg, a point of infinite density. And then, that egg exploded and released all of the stuff that would go on to become the universe. That is easy enough to picture, and it makes enough sense. If everything is currently expanding, then if you run that in reverse to go back in time, then everything would contract, and eventually it would return to one single point. Only this is not true. The universe didn't expand from one single point like an exploding grenade. Remember our bubble, the cosmic microwave background, the light from the Big Bang. It surrounds us in a perfect sphere. So, the Big Bang didn't occur in one place. It happened everywhere to everything all at once. We don't know how big the universe was pre-bang, but we're pretty sure that it expanded from that size to its current size in an instant, a tiny sliver of a second. And in that time, an area of space the size of one grain of sand might have expanded to the size of a galaxy. So if the pre-bang universe was a sandbox, then try and imagine every grain all expanding to the size of a galaxy all at once. And that is still nowhere near the scale of the universe. But try and think of it as one small step towards beginning to comprehend it.